Swayam Prabha. Digital India. Educated India.
Welcome to the 15th lecture in mechanics of materials. In the last lecture we saw 6 different material parameters: Young's modulus, Poisson's ratio, bulk modulus, shear modulus and 2 Lamé constants. Okay. The relationship that we obtained between these various constants is tabulated here. Again basically you had Young's modulus related to the Lamé constants, Poisson's ratio related to the Lamé constant through these expressions, and Lamé constant related to the Young's modulus and Poisson's ratio through these equations. Now what we are going to see is what are the restrictions or what are the possible values that these material parameters can take. Okay. Now what we define for the Young's modulus is, we define the Young's modulus as axial stress by axial strain, which was P by A into delta B into L, right. Okay. So now what happens if I apply L and A are positive, L is positive, A is positive. If I apply a tensile force, I should get a displacement in the direction of the force, right. So P by delta B must be positive, because the displacement should be in the direction of force. If I apply a compressive force, the length will reduce, delta B will be negative. If I apply a tensile force, P will increase and delta B will increase, will be positive, and hence P by delta B has to be positive. Okay. From these restrictions you find that Young's modulus has to be a positive number. Okay. Now the question is, can Young's modulus tend to infinity? If Young's modulus tends to infinity, what you are saying is, even though I am applying an axial stress, tensile or compressive, there is no strain developed. That is the meaning of E being infinity, which is a rigid body. E tending to infinity means the body tends to become rigid, that is there is no deformation even though I am applying a force. Okay. That is the displacement between two particles is the same irrespective of what two particles I consider in the body. Okay. So since in this course we are not interested in the rigid bodies, what we say is the Young's modulus has to lie between 0 and infinity. It cannot be 0, it cannot be infinity, but it has to lie between 0 and infinity, or it can be a positive number. Okay. A similar argument we make for the shear modulus. Shear modulus was defined as shear stress by angle change caused due to the shear stress. So a shear stress acting like this on a body should produce angle change in the direction of the stress, right. A shear stress acting like this should produce an angle change in the direction of the stress that is acting. Okay. So G has to be positive for the same reasons that displacement has to be in the direction of the applied force. Displacement has to be, since displacement in the direction of the applied force. Okay. Again shear modulus being infinity means, shear modulus tending to infinity means there is no angle change despite there being a shear stress applied. Infinity means no angle change despite shear stress acting. Okay. This means the body is a rigid body, which we are not interested in this course, because we are interested only in deformable bodies. So, the range of G is this, it has to be a positive number. Okay. On the other hand, bulk modulus is defined as the ratio of hydrostatic pressure divided by volumetric change. Okay. Now, again bulk modulus has to be positive, because if I apply a compressive force, the volume should decrease. If I apply a tensile hydrostatic pressure, the volume has to increase. Okay. For the same reason as above, K has to be greater than 0, since displacement in the direction of the applied force. The applied force. Okay. Now, there are some materials which will not change its volume despite what hydrostatic pressure you apply or whatever be the stress state. There are certain materials that will not change its volume. Okay. Such materials are called as incompressible materials. Reals, the volumetric strain is equal to 0 for